Record. We can get started. Great. So we talked about invitational learning and we saw that it was reasonable but expensive and sometimes hard to scale to long horizons. And we started talking a little bit about policy gradient. And so today what we'll try to do is finish the rest of policy gradient. And then next class we'll focus on active critic methods and approximate dynamic programming. Right? So what we want to do is do the simplest possible technique for reinforcement learning, which is doing gradient descent on the policy learning objective or on the expected reward objective. That's policy gradient. We talked a little bit about some algorithms. We'll recap them. We'll talk about why it's not perfect. We should use a better method, and keep going. Yes. All right. So if everyone remembers, our objective in reinforcement learning is to infer the parameters of a policy by theta, such that the expected sum of rewards or discounted rewards under that policy are maximized, right? And so we kind of had three different techniques we could use to solve this. We have gradient descent. We try to just take this objective, take the gradient on it to a set. There's dynamic programming, which we'll cover next time, which is Q learning, active critic, and these methods that try to use the Markov structure of your problem. And then there's model-based optimization, where you try to learn an approximate model of your environment and use that to optimize your reward. And we've kind of been focusing on gradient descent so far. So I'll do a quick recap of what gradient descent looks like. Then we talk about why it's bad and how we can fix it. Yeah. Okay, so what we really want to do is we want to take the gradient of our objective. So J theta is our objective, which is the expected sum of the rewards. They made it with it. So we want to take the expected sum of the rewards to the gradient. And we saw that last time the gradient is going to be grad log p theta tau times the sum of the rewards of the predicted. So can someone remind me how we actually derived that? Like, how did we get from, let's see. We defined J theta as the expectation of tau from P theta tau, R tau. And then we derived that the gradient is the expectation tau from P theta tau, grad theta log P theta tau, R tau, right? And we took this jump from here to here. Can someone remind me about it?
Well, after we pull the gradient in, we did the reinforcement where we multiplied and divided by tau.
Perfect. So we took the gradient, we moved the gradient inside, or actually that doesn't make sense here. Let's write it properly. We wrote this as P theta tau, R tau. We took the gradient, we moved the gradient inside. So we got grad theta, P theta tau, R tau. And then we multiplied and divided by P theta tau. And then by P theta tau, we got P theta tau R tau. And then we use the chain rule, right? Or the inverse of the chain rule to say this is going to be P theta tau, grad log, P theta tau, R tau, T tau, right? And that's exactly what this expectation is, right? So that's kind of how we got here. So just to recap, we defined what our objective is. We moved the gradient inside. We multiplied and divided, and we used the inverse of the chain rule, right? That's really all we did. Everyone with me? Does that strike a bell? Okay. So the reason we did this is we wanted to evaluate this as a Monte Carlo estimate so that we can implement it in code, right? So we said that we can approximate this using samples. So you just sample things from your policy using a statistical sampling. You compute the grad log phi's, you compute the sum of r's. You increase the likelihood of actions in high reward trajectories and push down the likelihood of actions in low reward trajectories. You just average this over samples, and that lets you implement it in code, right? And so we went over, I'll refer you to the last lecture for the code. It's basically you just take, you do supervised learning, but you multiply it by the sum of rewards to get you. But that's kind of a recap of policy gradient. Okay, so before we get further, why might this not be good? Like what might make this challenging to apply to practice? High variance, right? So the issue here with this algorithm is that there's high variance, which means it's hard to tell what matters without a lot of samples, right? And so because you're using a single sample estimate, you're just saying you weight by the sum of rewards in the current trajectory. And the current trajectory is susceptible to, coupling together of all the actions. It's susceptible to lucky or unlucky samples. It's susceptible to scale variations. You have high variance, right? And you can combat high variance with huge numbers of trajectories. And in some domains, that's okay. Like in Markov-Hutter's domains, you use a huge number of trajectories to trade in sim. But if you're like doing RL in the real world for a robot, it may not be okay, right? So we need to find a better way to reduce variance, right? So the problem of variance is basically saying that like, if you like run multiple, let's say you have a small number of n, if you run multiple trials, you'll get different results, which means that your variance is going to be really noisy. And so if you want to reduce the noise in your gradient, you need to just take a huge number of samples, right? And so variance directly correlates to sample complexity. So the less variance you like, basically you need to have a gradient that points in the right direction. And if you have a high variance gradient, that means you need to have a huge number of samples to get a to get a more accurate estimate of your gradient, right? So essentially high variance means huge sample complexity. That's the effect of high variance, right? So this is what makes policy gradient often unstable, because unless your batch size is ginormous, often you'll have different time steps giving you pretty different gradients. And one of the papers you all will read will kind of analyze the variance of the gradients. And so this requires huge numbers of samples, huge batch size, which makes it hard to train unless you're in simulation, right? You have a single robot running in the world, how much can you collect? Okay, so does that problem make sense as an issue with reinforcement learning or with policy gradient? So we talked about the first way we can deal with this, which is saying that currently, if you look at the objective kind of goes from t equal to 0 to t prime equal to 0 to t, which means that you like sum up rewards in your entire trajectory, even the pass. So let's say you're like considering t equal to 10, right? You're considering grad log 5. It's weighted by the sum of reward from t equal to 0, t prime equal to 0 to t, which means that like the grad log prob at time step 10 is being affected by rewards at time step 0 to 9, even though that like cannot affect what happens, right? Or as in the action at time step 10 cannot affect what happened at 0 to 9. So it really shouldn't affect anything, right? So the first thing we did was we said that this includes things in the past, so t prime less than t, right? And that's like not going to be affected by your action at time step t. And hence you can like kind of cut them out, right? So you can say that your policy gradient is only going to depend on the weighted sum of rewards is only going to be computed from your current time step t till the end of the time horizon. You can do this with discount as well, but the point is that you are just not going to consider the past. And this goes the Markov property, that like you your action at your current time step is not going to affect things, and like it's not going to affect things in the past. You just care about doing the best you can in the future, given where you are. Okay, so all we're going to do here is you're going to have like, you can think of this as 3 for loops, right? The outer for loop samples trajectories, the inner for loop goes along time steps, and then the innermost for loop goes from the current time step to the end of the horizon, right? So when you implement this, you're kind of going to have 3 for loops, like one that samples trajectories, and then one that computes the grad log prop for every time step and every trajectory, and one that computes the return to go from that time step till the end of that, right? And so you can use like NumPy has some like cumulative sum features that make this efficient. So in your homework, you'll use that. Yes. So all we did is we said, don't couple the effect of the states that are in the past, just consider things in the future. Yeah. Okay, so that's what you're going to call return to go. So a return to goal could be thought of as just like sum of rewards in the future, starting from the current state, and executing your policy. Okay, so what we're gonna kind of try to study today is these four things. We'll see how far we get. But we're gonna start by, we talked about reducing the variance with causality, right? Just like future can't affect the past, given the present. We're gonna talk about a different way of reducing variance with these things called baselines, right? And then we're gonna say that that helps reduce the variance, but there's other problems with policy gradient where they're sensitive to parameterization, which means that you change the parameterization, the gradient changes. And so we'll introduce a technique for what we're going to call covariant parameterization, which is a natural policy gradient. And that's going to basically allow your updates to be far less sensitive to the choice of parameterization. Then we're going to talk about how natural policy gradient is kind of impractical to implement. And so we're going to come up with a method called trust region policy optimization. Okay. So we're going to talk about trust region policy optimization, which is a practical way to implement insights of natural policy gradient. Then we'll talk about proximal policy optimization, or PPO, which is king, right? That's how you solve all problems in the universe. And so, yeah, that's going to be our outline. We'll see where we get. Yeah. But okay, so we talked about how we couple together the past with the future. But there's another problem in these policy gradient updates, which is that they're susceptible to scale variations. So what I mean by that is, let's consider this like this plot, right? So let's say we have trajectories here. We're gonna like plot the density of our policy. So let's say the policy is gonna say have highest likelihood of this trajectory. This is just a schematic, just to explain. The policy is gonna have highest likelihood of this trajectory, and we want to like get some samples of different trajectories and update this trajectory distribution, right? So this is the distribution of our current trajectories. We want to sample some rewards. It's not a perfect distribution. We want to take a policy gradient to adjust this distribution over trajectory. Right? And so the first thing we might do is we might run these things in the environment. We might get like two samples with say, okay, this is like a little bit positive and the trajectory here is quite negative. Right? And so what's going to happen if we treat these as our rewards? This is our, you can think of this line over here as p theta tau, like our trajectory distribution. These are our rewards. So like think of like the height of them as the reward, right? So these are a little bit positive, these are quite negative. Right? So what's going to happen to your policy distribution? Like it'll shift away from the negative, right? So it's going to go much closer to be positive. It's going to really push down the negative, right? And so it's going to go over here. Now, if I like just added a constant to all of these returns, it shouldn't change my gradient, right? Like the gradients shouldn't be affected by a constant. But if you add a constant to everything, right? What's going to happen is now that you're going to have like all things are being pushed up, right? So you're saying that like things on the right are being pushed up and things on the left are also being pushed up. And what's going to happen as a result is that your trajectory distribution is going to only move a little bit, right? So if you look at, I should have put these on the same plot, but if you look at the previous amount of movement, right? It's saying you push down some stuff, you push up some stuff. And now what you're saying is I just added a constant to all the rewards and really shouldn't affect the gradient, right? So what's going to happen now is that everything's going to get pushed up, some less than others, right? And that's going to result in a different update, right? So basically just by changing the scale, you result in a different update. And primarily the reason is that when you think about like these, like if I had infinite samples, right? If I had infinite samples all over, then because the probability distribution is normalized and you're saying, okay, let's push up some stuff, but let's push up other stuff more. In a normalized probability distribution with infinite samples, like the appropriate things will be pushed down. But if I have a finite number of samples, I only have 3 samples, right? So from my perspective, I have to push this thing up and I have to push these things up. Right? And so with a finite number of samples, you'll get a different value of the gradient when you change the scale. And that's going to cause a problem, right? Because it leads to variance. Essentially, these two things, which should give me the same gradient, are now giving me different gradients. Right? So one way of thinking about it is, if I have rewards that are all positive, essentially this thing is much worse than this thing, and I might want to sample other things in the middle. But since I only have a finite number of samples, it's going to lead to a different gradient there versus here. Yes. So that's what's going to cause our like scale susceptibility. So you can think of it as like when I have like these arbitrary uncentered scale returns, like some of the rewards, they can lead to huge variance. Because imagine all your rewards are positive, you know, every action in your batch is going to be pushed up by some amount. And if I had infinite number of samples, this and this would be the same. But I don't have infinite number of samples, which means that these things will be different. Right? So when you talk about variance, it's about saying that you have a limited number of samples, and it's going to lead to, depending on which samples you took, it's going to lead to different outcomes. Right? So how do we fix this? Don't look at the second one. So one way you can fix this is that whenever you have returns, you can always try centering them. Right? So you're saying that, okay, you have different scales leading to different gradients. An easy way to like not have these things be different is to say, I'm never going to consider these like unnormalized, uncentered returns. I'm always going to try and say, center the returns to something like the average return. So some things that are, you know, better are pushed up, and some things that are worse are pushed down. Right? And so all that this is going to do is it's going to say that, you know, I'm never going to consider things like this and things like this as separate. I'm always going to like recenter them, right? So I'm just going to try and subtract some like mean value, let's call it B, right? And so this is going to like shift this guy down, shift this guy up, so that they kind of like go onto the same scale. And if they go to the same scale, then you don't have like as much variance in your gradient. Yeah.
Are you updating the as you see more samples?
Yeah. Yeah. So we'll talk about what B should be and how we can like probably say things about it. But yes, we update B with more samples. Yeah.
So to be clear, what you're doing is like making them go either like above or below that axis the same amount.
Yeah, so you're trying to subtract like a constant from those guys to like normalize them. So you subtract it from all trajectories. And like for these guys, you like add an amount so that you bring it to like the same scale. But relatively across trajectories, they're gonna be like you have to subtract the same thing. Like you can't subtract like 10 from the thing on the left and 50 from the things on the right. You have to subtract the same thing because their relative importance has to be the same. Right? So my point is that I can't just like arbitrarily take this return. I can subtract a constant from it without changing things, but I can't like subtract 10 from here and 50 from here.
I thought
Because that changes your objective.
I thought they were susceptible to scale variation. Because you said subtracting a constant doesn't change it.
Yeah, so what I'm gonna do is I'm gonna like imagine that I had two different states with like different return values. Like in state one, the return values are from 0 to 100, and state two is from -500 to -400. What I'm going to do is I'm going to, in both cases, try to like bring it between -50 to 50. Right? And so then like everything kind of lives in the same scale.
But for different states, once you like for example, in some states, isn't it like probably only possible to like get very low rewards? You're basically just like in some states, it's like giving like making your reward very negative for all actions.
Yeah, totally makes sense. But I guess you have to remember that the policy gradient, what it's doing is it's saying that at a particular state, if you have many different actions, you're like just trying to reweight relatively between those actions. It's not saying that like this state is better than this other state, right? So it's more like saying you sample a bunch of actions and then you choose the best amongst those actions, rather than saying you choose the best amongst the states. Right? So like on an absolute value, this state could be like -500, this state could be like 200. But all I want to do is pick the best action here and pick the best action here. So it doesn't like, it's not that I still need to care about the bad state because I need to get from the bad state to the good state, right? So I can't just like ignore that bad state. Okay, so what we're going to do is we're going to like as you probably alluded to, you want to have that like centering factor be state dependent, right? So like for a state where the rewards are from -400 to -500, that's going to be a different number, and states are from 200 to 300, that's going to be a different number, right? And so what we're going to do is we're going to take our sum of rewards in the future, our return to go, and we're going to subtract a state dependent quantity B of ST, which we're going to call our baseline. And so B of ST is going to be our baseline. The important thing you need to remember is that the baseline does not depend on T prime. It only depends on T. So it's basically saying that, like, we did this thing where we sampled a bunch of different trajectories, right? For some time step T, we run our like T prime thing to compute the like sum of returns in the future. And what we're going to do is we're going to subtract a B of ST, which depends on this thing, but not on this thing, right? So it has to depend on the time step T for which you're taking the grad log probability, but not the sum of rewards. Right? So that's what we call a state dependent baseline. So it only depends on your current state, not on future states or actions. And so what you're saying is that, like, imagine there was S1 and S1 had some reward distribution. And S2 had some reward distribution. Maybe this is not the best visualization. Let's say S1 was rewards from -400 to -300, and S2 was rewards from minus or like 0 to 100, let's say, right? What we're going to do is we're going to have a state dependent baseline that tries to bring this one, like, we're going to have a different value at B of S1, different value of B of S2, and this is both of them are going to try to be brought into the -50 to 50 range, right? And so the important thing is that the state, it can be a constant too, but it's more effective when it's state dependent. But it depends on this state and not the return to go. Yeah.
So BFST depends on the state and the time that you're at the state.
Yes.
And so wouldn't it be expensive, like an accurate feed of ST?
So often what you do is you have something that is stationary. So you just have something that depends on your current state, but not on the time. So you just like feed in the current state into like a neural net, it just outputs a scalar, and you learn that. So you don't have to like recompute every time, you just have a neural net output your BFS. Your BFS is represented as a neural net that goes from ST to like a scalar. And we'll talk about exactly how to learn it in a second. Okay. So I did this. Yeah, bro.
For one state, if I'm taking the worst possible that, if I minus like the first one, the cost should be much higher than I'm taking the worst possible action, second one. So by doing this, are we sort of changing that in the environment, like we are sort of giving more preference to a very bad state?
So I think the important thing to remember is that you're at that state anyways. So you're either going to incur -300 or you're going to incur -400. So relatively, the amount of extra regret you incur is like not that much worse. So let's say I'm at state S1, right? And my state S1 is going from -400 to -300, right? So best case, I get -300. Worst case, I get -400. But like I have to make a decision at S1. And so this is not a question of whether I reach S1 or not, right? That is determined by previous steps. This is saying, if I'm at S1, what should I do, right? And then you're saying there's S2, which is, let's say, let's make it even more extreme. This is like 1,000 to 1,100, right? So it's saying, the best possible outcome is 1,100, but the worst possible outcome is 1,000, right? So like, the important thing to remember is you're trying to decide, the policy is saying, if you were at S1, what would you do? Right? And so the relative difference between the worst case and the best case is 100 in both cases, right? Important. So you don't want to like, you can't like multiply your things by arbitrary numbers. Like you can't scale the return to go by different numbers per state. That would make things messy. Okay. So, oh, sorry.
So then like, if we're subtracting some constant, right, doesn't that mean like if like our rewards were some like if we sample like from like t equals 2 and our rewards are like all like really high, so we're gonna be forcing some rewards meeting.
Yes.
But like, doesn't that like, do we necessarily want to be pushing like good actions? In a sense, like deprioritize them?
Well, if you're like you're trying to choose a normalized probability distribution that's picking between the best possible actions, right? So it's like, if everything, let's say everything was like 100, right? Then the B of S, let's say the B of S is your average reward, then it's just gonna say, don't change anything. Let's say your policy was already always outputting 100, that's the best possible reward. This is just going to be average, which means this is going to be 0, which means that you don't change anything, right? Yeah. So in that case, it doesn't matter. I guess what you're saying is like, let's say you had some good actions and some even better actions. I guess what it's saying is that you're going to sacrifice the good actions for the sake of the even better actions. Because you have like a finite amount of probability mass that you're going to distribute. You should distribute to the things that are highest. So it doesn't matter if it's like the absolute scale doesn't matter, just the relative scale matters. Because you just want to get the thing that is best.
I see. So does this mean you have to train for longer?
The hope is that you train for shorter, right? Because it's like saying that the gradient is less noisy. And so you're like, you've seen how gradient descent curves go, it's like, right? So it's going to try and like reduce the noise in your gradient so you train for less time. Okay, so what we've done here is we've like subtracted this B of SC, right? So B of SC, I just like changed the objective. I like took my grad log pi and then I like subtracted a random B of ST from it. And so I like just made up something, right? What we need to figure out is, okay, we're gonna like intuitively at least, we've said this reduces variance. We'll try and work out why it reduces variance. But I guess the more important question is, I just like subtracted a random thing from a thing we derived from a principal method. Like, why is this okay to do? Right? And so what we're going to try and figure out is, does this increase bias? Right? So does this like, this was basic, I derived this as the gradient of the expected reward. And then I just like added a random minus B of ST. Kind of crazy thing to do, right? And so the question we want to ask is, like, does this lead to the same gradient and expectation? Like, does this give us an unbiased estimator? Right? How many of you all are familiar with unbiased estimators? So basically we want to see, does this increase bias? So what we're going to try and prove is that this objective is equivalent to the original objective, but with lower variance. Okay, so what we want to show is that this gradient, right? This is just, you can think of this as just like the stationary distribution version of policy gradient, right? So just saying you're taking expected S and A from your P, ST, AT. You're saying grad log pi, and then you're summing R, let's call it R, return to go, and you're subtracting B of ST, right? This is the thing that I'm proposing. The original thing that we talked about was basically that without the baseline subtracted, and I want to show that these two things are the same in expectation. Yes, and then it's unbiased. So let's kind of walk through how we're going to derive this. So what we want to show essentially is that you can separate out these two terms. You can say that it's going to be a product of the sum of reward minus a product times the baseline P of ST, right? And what I really want to show is that that term is 0, right? Because if I can show that the second term is 0, then I've shown that this gradient in expectation gives me the same thing as this gradient, right? And so it's like unbiased. And so it gives us the right thing, but it reduces variance. And so we want to show, essentially what we're going to try and show is we're just going to analyze this particular term, and we're going to show that this term is 0. Yes, everyone with me? So just to recap, we've taken policy gradient. We've said, okay, it's as a scale problem. So we're going to subtract out the baseline B of ST. B of ST is the state dependent baseline. It's going to like recenter the returns everywhere. And we want to show that this is not a crazy thing to do. And so we're first going to show that it doesn't change your gradient and expectation, right? And then we'll talk about variance of this. Okay, so we're going to do that by showing that the second term is 0. So, okay, so we have the second term. You can think of this as the expectation of grad log pi times b of s. Right? So let's try and expand this a little bit. Right? So we can say that this is going to be, this is your stationary distribution under your policy. So you can always write a stationary distribution as the marginal distribution times the conditional of AT given ST times grad log pi AT given ST times B of ST. Right? Yes.
When you say stationary, why are there still the T subscripts?
You're right, that shouldn't be. That's good. No T. Okay. I'll correct this on the slides. Yeah. Thanks for pointing it out. Okay, so you can write this as P of S times pi A given S times grad log pi A given S times B of S integral ds dA, right? And so essentially what we want to do is we want to show that this thing is 0. Right? So let's try to, one thing I try to do with proofs is that I want to get this to be 0. How can I get it like how do I get this thing to be 0? Like how do I I try to work a little backwards. So how do I this is a gradient of something. What do I make it the gradient of so that it becomes 0? A constant, right? And what do we know about probabilities? They sum up to a constant, right? So if I can somehow convert it into an integral of a probability distribution, you get a constant, and then you'll get 0. So all we're going to do is try to work backwards and try to convert this nasty little thing into something that looks like the gradient of a constant. Okay, so the first thing we're going to do is we're going to say, we're just going to go back and flip that chain rule again, right? So we can say that, grad log pi, so this is going to be pi times grad log pi is going to be 1 over pi times grad pi, right? D of st or dst dat, right? So all I did is use the definition of the gradient of log, right? Same chain rule, same as before. Now what I can do is cancel these guys out. So I can rewrite this objective as P of st times grad pi at given st dst dat. It's going to be s, right? All I did is I reused chain rule to go from grad log pi to 1 over pi times grad pi. Sorry? No, it's there. Sorry. It's it's very badly written, but it's there. This thing is the B term. You see it? Huh? Oh, good. So attentive. You guys are great. Yeah, thank you. Appreciate it. Good. Okay. Yes. Thank you. So we lost the B term, but now we have regained it. And so, okay, so this is going to be this integral. You notice that this term and this term just don't depend on A, right? So just take them out of the inner integral. So you can write this as integral S P of st B of st times the integral A grad pi at given st dat, and then this whole thing is dst, right? All I did is I took the things that didn't depend on A outside the inner integral, and so we said, hey, this has no A in it, hey, this has no A in it, take it outside the inner integral, right? And so these two sit in the S integral, and then you only have this term that depends on A, which is in the inner integral, right? I know we're in the weeds, but I think it's useful for us to figure out. And then I'll zoom out right after. But now, no, sorry. Okay, now, what we're going to see, sorry. What we're going to see is that I can, just how I pop the gradient inside, I can also pop the gradient outside, right? And so what I'm going to do is I'm going to say, this gradient is going to pop right outside. And so we can write this as integral S P of st B of st times the gradient of integral pi at given st the AT, the ST, right? And now we've got the integral of a probability distribution. That's going to be 1. Right, so this thing is going to be 1. And the gradient of 1 is 0. And then like everything goes to 0, right? So beautiful. Okay, so now we can go from my terrible handwriting. No, sorry, my Zoom decides to like leave things on the screen every once in a while. I'm gonna have to stop sharing for a second. Good. Okay, so we can go from my terrible handwriting to typesetting, so you guys can read it more carefully. But essentially, just to recap, what we did is we said we're going to write the stationary distribution as marginal times conditional. So it's going to be likelihood of the state times likelihood of the action given the state. Then we're going to take all the terms that didn't depend on A outside, right? So we're going to then use the chain rule to write this as 1 over pi times grad pi. So you just get grad pi, and then you like, just like you pop the gradient in, you can pop the gradient out. Okay? So you pop the gradient in at the start, like when we're doing policy gradient, you can similarly pop the gradient out. And so now you have the gradient of the integral of a probability distribution, which we know is 1. Okay? So then you have gradient 1, which is 0, and then your whole term goes to 0. Right? So intuitively, you can think of this as saying like, because you're just subtracting, because you're just normalizing scales on the current state, and you're not doing things that are in the future, like this whole thing is not going to work if ST depended on AT. Right? You cannot take this outside, like none of this integrates out to 0. So this is what you, like if you read the literature, it's often called an action-dependent baseline. An action-dependent baseline, this is a state-dependent baseline. You could also have it depend on actions, and then none of this works. Right? So just because it's state, it's just saying you're just renormalizing based on state, but you're not using any information about the future to change things. And so that's not going to change your state, right? In expectation. And so kind of like zooming out to what we did is we said we're going to like subtract P of ST from the return to go. We're then going to try and show that that second term is 0. To show the second term is 0, we're going to try and convert this to the gradient of an integral of a probability distribution, which is 1. So you get gradient 1, which is 0. So this whole term goes to 0, right? So then the gradient and expectation is kind of the same. Okay, did that parse? I think like it's a little hard to like get all the details in class, but I just want you to get the high level idea and try and work it out at home. Right. So the high level idea being, we've subtracted the baseline the center. You just want to show that that thing evaluates to 0 in expectation.
Isn't it evaluates to 0 without the presence of B? B, which is 1.
Yeah. So B could be a constant, or it could be 1, it could be, yeah. So like 1 is a valid baseline, which is not going to affect anything. But the point is that a constant baseline is almost trivially going to evaluate to 0. A state-dependent baseline is a bit more interesting because it can be different for different states, right? And we're saying that it still evaluates. So that's interesting.
Earlier we had a summation for the videos, like summation of the rewards minus B.
That is, I think I should be a little more precise there. This is going to be a summation of, this is going to be a summation of rewards.
Oh, I see.
Because notice that this is over T and this is over T prime. Yeah. Yeah, but yes, exactly. So if you change, so there's like a really nice, I'll link some readings for you guys, but there's a really nice line of literature on what happens if you make, if you allow the B to be dependent on A, you can reduce the variance further because you know more information about what's going to happen. The problem is that it changes the gradient. And so what people do often is they try to like use P of ST, but then they like add a correction term that accounts for the bias that it introduces. And so like that's how people do it.
So you mentioned when you were saying it's a stationary distribution, but it doesn't need to be a stationary distribution.
You can derive this whole thing in the trajectory view.
So it's like for notation.
Yeah, it's just easier. It's easier to write without the like infinite number of integrals.
Yeah.
Cool. So to recap, we had two ways of we said variance is a problem. We have two ways of reducing variance. First is to decouple the past from the future, right? So just don't do return across the whole trajectory, just do return to go. And then the second is saying we're going to subtract the baseline from the return to go, and that's going to let us reduce variance without introducing bias. Okay. Now the question is, what should that B of ST be? Like I've instantiated B of ST as like this like abstract thing so far, right? What should it be? And so a natural thing, you can use B of ST to be anything. Some things are better than other things, right? Like Paul was just saying, we could make it a 1 and it's fine. It's just not going to reduce variance very much. Whereas you can make it something, you know, more informative and reduce variance more. So what people often do is that this is what you call the critic in PPO. So whenever you see a PPO implementation, the critic is often referred to as the baseline. So the word critic in reinforcement learning is used willy-nilly for a lot of different things. So like be a little careful when you think of a critic. But what often PPO and other algorithms will do is they'll say your value function or your critic is the same as your baseline, right? So this is going to be a baseline, and you're going to regress it to like the average sum of rewards, right? So you're going to say take every trajectory, compute the average sum of rewards, and just construct an optimization or just construct the sum of rewards and construct an optimization problem where V hat tries to regress to the sum of rewards, which is going to make it equal to like the average over the sum of rewards. So essentially, if I have like from ST, let's say I had one sample which said this was, 50, another sample said this was 0, another sample this says was minus 50, like the average sum of rewards is going to be like 0, right? And so often what you'll do is you just like sum up the rewards in the future, construct, this is often called a Monte Carlo regression, because you just sum up all the rewards in the future in a Monte Carlo way. And so this is just going to be, you can think of this as the average rewards, right? And so you just optimize a neural network or some function approximator that takes in your current state and regresses to the average sum of rewards.
So we're like all states or like or
Yeah, so often you'll do it on your like latest batch of data. But you like carry over, you typically will do it like fine tuning from the previous value function, which is on the last batch of data. So it's like kind of biased by the previous. So in practice, what you do is you like collect new batches of data, and then you like keep optimizing the loss function on the latest batch of data, but you won't reset the parameters of the type. You just warm start it from the previous. So it doesn't have to be just the latest, but like that's optimal.
like an average of how you're doing that.
Yes, exactly. But like your returns are just going to be dependent on what you're doing right now. So average on something else may not be as important. Okay, any other questions? Yeah.
It's the T started from the start of
Correct. So the what this I think you meant T prime in the second test. So the T is the current time step for grad log 5, and the T prime is what sums up rewards from now to the end. And so T prime is the return to go index, and T is like taking the grad log 5 at every single index.
What here,
This one or that one?
this one regression.
Right.
The T started from 1 to H is T from the start to end.
Correct. Right.
So the V has a SP.
Like,
right?
they need both.
Yeah. I think that's yeah. No, you're right. This should just be from T to the future. Yeah, that's a little type. Oof. Sorry, guys. That's my mistake. This should be like from, like, let's say T prime goes from T to H. That should be T prime. That should be T. Yeah, good catch. Man, y'all are super attentive this offer.
Or you could just
I guess the point is that for you just your value function needs to regress to the return to goal.
so it's also.
Yeah, exactly. So think of it as the value function regressing to the return to go. And when you're computing the value function, you just depend on the current state, not on the future. Okay. We'll do one more thing before we kind of break for a second, but we've talked about this thing reducing variance a bunch, right? But like can we characterize variance? Is there like an optimal baseline that optimally reduces variance, right? And so what we'll try to do is we'll try to like write out the variance of this estimator, and then we'll try to find an optimal baseline that optimally reduces variance. And we'll try to see if that makes intuitive sense, right? So what I'm saying is that basically you have an estimator here, right? And we want to compute the variance of this estimator, right? And we want to say that like different choices of B, like the variance is going to depend on B. B is in there, B is in the gradient update, so B is going to be in the variance term. And a particular choice of B is going to be optimal, right? And so we're just going to consider, for the sake of ease of derivation, we're going to consider a B that is a constant, right? Where it's not going to be like, let's just consider state, not a state dependent B, just a B that is a constant, and try to find the optimal B, right? So time invariant B that minimizes variance. Okay, and so this is going to get into the weeds, so don't stress if you don't get it. Just try to like get the high level intuition, right? And the reason I'm going into this is so that you can work out the variance of different estimators and try to like figure out which ones are lower variance than others. Okay, so the definition of variance is right here, right? And so given this gradient estimator, can someone tell me how we would write the variance of this estimator? So you have expectation. I'll write out the first term. You tell me the second term. You're going to have that, and then you're going to have grad theta log p theta tau squared, or that times r tau minus b, the whole squared, minus expectation. What should this be? Good. Okay. Yeah. Yeah. Oh. R tau minus b, right? And then you just have squared here. Okay, right? And so what we want to do, let's call this thing the variance. And this is really a function of b. We're kind of going to try and take d variance db equated to 0, right? We're just trying to find the optimal variance, right? So we're going to take the gradient equated to 0, and we're going to try and simplify this as much as possible. So let's try to see what we can do here, right? So the first thing to look at is if you look at this objective, right? This is just the policy gradient squared. And so what did we derive in the last slide that will allow us to like drop that second term? It doesn't depend on B, right? The gradient is the same, which means that this whole thing is basically expectation, whatever, grad log P times R tau, and it like doesn't really depend on B, right? So this whole term can like just be thrown away because it doesn't depend on B. Okay, so now we just have the first term. Let's, for the sake of simplicity, let's just call this G tau, so I don't have to keep writing grad log pi. And so now your variance is going to be expectation P G tau R tau minus B the whole squared, right? Okay, so now we're going to try and take the gradient of this thing and equate it to 0. Yes? So you're going to have 3 terms. You're going to have G tau squared RT squared. You're going to have G tau squared B squared. And then you're going to have G tau squared R tau B. Yes? Yeah, all I did is I just like expanded the square, right? So expanded the square, expanded this square term. You have two square terms and a minus 2ab term, right? So now if I want to take the gradient of this thing with respect to B, basically this term doesn't matter, doesn't depend on B. This term just becomes 2b, right? And this term, the b just goes away, right? So what you'll get is 2b expectation gt squared minus 2 expectation gt squared rt t or tau is equal to 0, which means that your optimal baseline is going to be expectation gt squared RT by expectation GT squared. Yes? So all we did is we took the variance, we expanded it, we took the gradient with respect to t, and what it gives us is this term which actually like pans out nicely intuitively, because it's saying that you're kind of taking the expected reward. And it's like the average reward, but you're weighting it by the like gradient magnitude. Right, so you're saying that like the things that have like higher gradient magnitude should be like weighted low. And so yeah, that's how you work out the optimal baseline and the variance of your estimator. And clearly this is not equal to 0. So this will reduce variance over not using a baseline. And so you can show that this, like using a baseline, mathematically reduces variance, right? So easy way to do it is take your estimator, write out the definition of variance, take the gradient with respect to p, find an optimal baseline. It's not equal to 0, which means that like there's a better baseline than no baseline. Right? This not? Because there's no p. Okay, so let's recap before we take a little break. We talked about causality, and we said, oh, we're going to subtract this baseline because it's going to center things. We showed it's unbiased in the previous section, and then we showed that we can reduce variance with an optimal baseline, right? Okay, before we get to the next stuff, let's take a pause, maybe 3 minutes, and we'll start again.
I saw the next slide was the animal.
Yeah.
Was that a video?
Yeah, this video.
I was too late to see the.
Question on what was the intuition behind the G equals whatever expectation?
Oh, it's basically the gradient magnitude. Let me drag this in here so that everyone can see it. Oh no, went to the start. It's easier to just do it with something we can look at, right? So you can look at this as maybe you can look it up. Right? So it's basically it's like we set it on a centered thing, right? Yeah. And so that is the expected reward, kind of centric. That's not accounting for like certain things have like a higher magnitude of gradient than others. So what it's saying is that like you expected reward by weighted by the magnitude of the gradient. That's just like things that affect the gradient weighted more, like things that affect the gradient more weighted more, things that affect the gradient less weighted. And so like that's going to account for not just the impact on the reward being average, but also on the impact on the policy price. Like this is affecting the reward and accounting for the impact on the policy price. So you can think of it as like almost like a softmax where you're like weighting the different by the events. And all that. Okay, so it's just expectation factors. You like sample, yeah. And so the thing that I derived on this previous slide is actually going kind of hard to compute with samples, because you have like one thing divided by another thing, and so like estimating sample wise is not actually unbiased. Okay, and so it's not that easy to do. And so this is a theoretical exercise, and mostly you just do average reward. Oh, so whenever you have like division with an expectation, it just makes every life hard. It's like the same reason that like in imitation learning, you have to like when you have this partition function, it's like hard to compute because you're dividing by like an integral or dividing by an expectation, and you can't estimate that with samples without being biased. Okay, so let's keep going. Right, so we kind of we can't take the fact that we're going to do gradient descent as like a given. We're like, oh, well, obviously, Stephen Boyd told us we should do gradient descent, so we should just do gradient descent, right? But let's see if that's the right thing to do, right? So, gradient descent, is essentially steepest descent on a linear approximation of your objective under the Euclidean method. So let's try and unpack what that means, right? So if I think of gradient descent, right, I'm saying that, okay, I have this objective j theta, and I'm going to do ascent on this objective, which means I'm going to say my theta I plus 1 is equal to theta I plus alpha grad j with theta equal to theta I, right? I kind of took that as a given. But this is, you can derive gradient ascent from the objective, from the like perspective of steepest descent, right? So what I mean by steepest descent is that if you take your objective, right, and do a linear approximation. So linear approximation is a first order Taylor approximation, right? So is everyone familiar with Taylor approximations? Right? So if you have j theta, you can approximate j theta. It's kind of like saying approximate with the linear function at that point, right? Saying approximate j theta as j theta I plus grad theta j theta I times theta minus theta I. That's your linear approximation. And you're trying to say that like you can derive, I'm trying to say that you can derive gradient descent from the perspective of taking this linear approximation to your objective and trying to solve for the best theta under a quadratic constraint. So that's saying is that assuming that basically you can like put a quadratic constraint on theta, right? Gradient descent can be derived from the perspective of solving the linear approximation with a quadratic constraint. Okay, so let's try and derive this, right? So the way we're going to try and derive this is we're going to say, we're just going to form the Lagrangian, right? So we're going to say, you're going to do max theta min some like lambda j theta I plus grad j theta equal to theta I, theta minus theta I, plus lambda theta minus theta I, theta minus theta I, minus epsilon. Something like that, right? That's all I did is I formed the Lagrangian, right? So I said that I'm going to take the constraint. I'm going to form the Lagrangian. To derive gradient descent, it's easiest to just think of this as a penalty method with a fixed lambda, rather than something that solves for lambda. So let's just say we're just going to fix the lambda to something, right? And then you're going to try and take the gradient of this objective. You're like, you want to find the optimum here, right? So you want to say, take the gradient of this objective and equate it to 0, right? You're trying to say, we've taken this is our constraint optimization problem. We want to find the theta which satisfies the quadratic constraint from the current theta I, while doing steepest descent on on a linear approximation of j theta, right? And so if you do that, then you can like take this objective and like take the gradient of this with respect to theta, right? So which terms depend on theta? This term depends on theta, and this term depends on theta, right? So what you can show is that 2 lambda theta minus theta I plus, I think I got the sign wrong here, it's a minus, plus grad j theta equal to theta I is equal to 0. Yes. So all I did is I took my objective, linear approximation quadratic constraint, forms a penalty method, take the gradient of this. So this term is a quadratic, so it's going to give me 2 lambda theta minus theta I. This term is a linear on theta, so it's just going to give me grad j theta, right? And so what I'm going to get is just like equating this whole thing to 0, I'll get theta is equal to theta I plus 1 over 2 lambda grad j theta equal to theta I, right? Call this thing alpha, and then you get gradient descent, right? So you can show that gradient descent is theta I plus alpha grad j theta at theta I. Right? That's literally the expression for gradient descent. You can also express it as steepest descent under the quadratic constraint. And so saying that assuming that the parameters are, you know, constrained to be in a quadratic ball from the current parameters, like what is the direction of steepest descent? Does that make sense? And so all we did is we formed the penalty method, did the gradient, equated to 0, and then that gives us gradient descent as an output. Okay, so this is how we derive gradient descent. This has nothing to do with RL. This is just like gradient descent as an optimization method. So gradient descent is problematic for two reasons, right? Amongst others. One is that if you like don't pick the step size carefully, you can like lead to like bad outcomes, and especially bad in RL. But basically, if you don't pick the step size carefully, you can like overstep the optimum, right? And so often like step size selection is a big problem in gradient descent based methods. So often you have to use really small step sizes, which makes it slow. And the other problem is that it's extremely sensitive to policy parameterization. So what I mean by that is like, you can like reparameterize your policy a different way. It's essentially the same expressivity, different parameterization, and it'll give you like different gradients. And so it becomes extremely sensitive to the choice of parameterization. And that like leads to high variance and instability, right? And so there's many ways to drive natural policy gradient. I find this the most intuitive. But essentially, when you have a big deep neural network, you don't have like fine-grained control on the choice of parameterization. And so if you're really sensitive to their policy parameterization, then that's not great for
By parameterization here, do you mean like the policy class that you use?
Yeah.
Or just the actual?
like I mean like the weights of your neural network. So let's look at an example for what I mean by this, right? So let's consider a simple loss function, right? Your loss function is theta1 plus theta2. And your parameters are theta1 and theta2, right? And so if I take the gradient of this thing, right? The gradient is going to be 1 with respect to theta1 and 1 with respect to theta2, right? And so what that means is I'm going to like step theta1 by alpha times 1 and step theta2 by alpha times 2, right? Now let's consider a different parameterization, which is saying like, let's reparameterize this whole problem by this phi1 and phi2, right? And so now phi1 is going to be theta1 squared. Phi2 is going to be theta2 inverse. And so I can rewrite my original objective theta1 plus theta2 as the square root of phi1 plus the inverse of phi2. These are like the same objective, right? So all I did is I like reparameterized my objective. Yes. And then I can just re-express from this objective, I can say theta1 is equal to the square root of phi1 and theta2 is equal to phi2 inverse, right? And so the objective theta1 plus theta2 can now be written as the square root of phi1 plus phi2 inverse, right? And so all I did is it's the same thing. I just reparameterized the choice of parameters, right? And so what happens then is that if you compute the gradient of this thing with respect to phi1 and phi2, what do you get, right? You get 0.5 phi1 negative 0.5, and you get negative phi2 to the minus 2, right? And so this is the basic derivative. But the point is that when you convert them back into like how the thetas change, the thetas didn't change by 1 and 1. Right. And so what I did is I just changed the parameterization. Like it didn't change the expressivity of the problem. I didn't change anything else, but it like massively changed what the gradients look like. Right. And so, and this is what you call like parameterization that's like, it's not a covariant method in that it's like not able to deal with a change in parameterization, even if it doesn't change expressivity. Right? So it becomes, what I mean by this is it becomes really sensitive to particular types of particular parameterization. And if certain parameters dominate in magnitude, they like dominate the gradient, right? And so an intuitive way to think about it is when you like think about things being in the Euclidean norm, right? What it means is that every parameter is weighted equally, right? And so you're saying like, okay, you have all these neural net parameters, they're all weighted equally, but if certain parameters are just like inherently way bigger than others, they're like weighted higher irrespective of their effect on the output, right? And so the problem is that it kind of leads to gradients that aren't covariant to different parameterization, then it's like susceptible to certain things being really large. Right? So you can think of this as like the Euclidean norm is equal across all dimensions, right? Even if it doesn't affect the output in the same ways. Or even if it does, so if you have a large thing that affects the output in the same way as a small thing, the large thing will be weighted higher than the small thing, which is a problem, right? Yeah.
So what does covariant mean?
Covariant, I just mean like you change the parameterization and it doesn't change the output. At least that's my interpretation.
You should not speculate.
No, it's yeah, it's a natural, like there's a whole line of work on natural gradients in general, right? So another way of interpreting this issue is that there's like your choice of parameters, and then your parameters kind of parameterize a function, right? And then the function is the thing that goes from X to Y, right? Like whether it's reinforcement learning is taking states to action. Predictors or regressors are taking X to Y, right? And your problem with gradient descent is that this like norm of the parameters doesn't account for how thetas actually affect the outputs, right? They're just like you can like change the parameterization so one thing is like 100 times bigger than the other, and it's going to like bias the gradient way more towards one direction than the other, right? And so ideally, really what you want to take into account here is something that like accounts for the effect of the parameters on the output, not just like their magnitude on an absolute scale. Like nobody cares about their magnitude. I can like scale them by 10,000, and only thing that really matters is their effect on the output. And so the important thing with gradient descent is that it's like, it's maybe like understood by this figure. It's like, in this figure, you can think of like this parameter is like stretched more than this parameter, right? If you think of those as your two parameter directions, it's saying like, let's say this was theta 1, this was theta 2. Theta 1 just was like stretched more than theta 2. And so you're now susceptible to like the increased magnitude of theta 1, even if it didn't affect the outputs that much, right? And so what you really want to do is try to convert this problem into something that looks more like this. That is like weighting things by how much they affect the output, right? And often this is called like the curvature of your problem or second order information, things that basically say how do, like you want to be cognizant of the like effect of your parameterization. And so that's the main idea here. And I find this example to be really informative in that it's like change the policy parameterization, the gradient change, not good, right? So we want methods that don't do that. Okay, so before I go to the next slide, because I goofed up the animation those things. How should we do that? So let's go back to gradient descent. And I want to like change this so that I can like, account for different parameters having different magnitudes and so on. How do I change the steepest descent objective to do that? Right. Yeah. So essentially what you're going to do is you're going to do something which does scaling, right? So you're just going to say that rather than an unweighted quadratic constraint, you're going to like weight it by a matrix G, right? And so your matrix G, you can kind of think of it as like it imposes a norm on your space, which is going to weight certain things higher than other things, right? And so essentially what you're saying is that if your original parameterization was this, your matrix G is going to like reweight it to look more like this, right? And so we'll work out what exactly the gradient looks like, but intuitively, all we're saying is that SGD was steepest descent under the Euclidean norm. And we are now saying we are going to do steepest descent under not the Euclidean norm, right? Under the G norm. And so you can also think of this as theta minus theta I sub G. That's often how you write it, right? And so the point is that you've changed the norm. And so now if you choose G carefully, then you can like account for this like parameter imbalance type situation, right? And if G is like properly adaptive to different choices of parameterization, then you can like your G can account for the problems that we saw in the last slide, right? And so the question becomes, one, how does this G affect the gradient update? And two, like, how do you choose G? Right? And so the way that affects the gradient update is you're just going to get gradient descent weighted by G inverse at the start. Right? And I'll go over it really briefly, but you guys should work it out on your own. Basically do the same thing that we did last time, right? So we say the objective is J theta I plus grad J theta times theta minus theta I plus lambda. But now you're going to have like theta minus theta I transpose G theta minus theta I. Right? So you just have this G term here, right? And so when you like take the gradient here, oh, I always mess up the sign. Sorry. When you take the gradient here, you're still going to get grad J theta, but you're going to have like this like G term, right? And so well, you can like move this to the other side and say grad J theta I is equal to G theta minus theta I. You multiply both sides by G inverse, right? So you can get, sorry, I'm not doing a good job of board management here, but one second. How do I not good. Okay. Okay, so let's say we started with this thing. We said okay, so this is our thing. We said 1 over 2 lambda times J theta is equal to G times theta minus theta I. Multiply both sides by G inverse, right? So you're going to get you're going to get 1 over 2 lambda times G inverse J theta I is equal to theta minus theta I, hence your update, right? So it's going to be weighted by G inverse. And this is often like what you'd refer to as your like curvature. This is often what you refer to as your curvature, or your G is basically inversely weighting the directions of your gradient, right? And so you can think of it as like the directions that are overrepresented in the gradient, right? Because your gradient is under the Euclidean norm, your G kind of like accounts for their magnitude. Right? So if you choose the G carefully, you can downweight the things that are too high and upweight the things that are too low. Yeah.
This might be not like the most direct correlation, but when I learned about regularization.
Yes.
In terms of like optimization, kind of like this in terms of like stretch dimensions, you kind of want.
Yes.
Like everything, is that like?
Similar, yes, very similar, very similar. You can also think of this as like, if you've seen Newton's method, right? Newton's method is very related in that Newton's method will take your gradient and like weighted by the inverse section. And so it's like a second order method, which is trying to find roots of your model. It's going to say your gradient is weighted by the inverse Hessian, which is like the second derivative of your objective. And so essentially what it does is it like accounts for this like the parameter like variance across dimensions.
The picture of like the parabola.
Yeah, so I think that so you have to be a little careful there. So the parabola and the line thingy, right? So you can think of this as your parabola. This is your linear approximation to your objectives. You're not changing the fact that it's a linear approximation to your objectives. So you're still using a line. But earlier, what we were doing is we were using like a Euclidean norm, right? So a Euclidean norm is essentially it's like drawing a circle, right? And now what you're saying is that you're using a G norm, and the G you can think of as like a rotated ellipse, right? And so you can say that your constraint, like when you think of this geometrically, you can think of this as like you're trying to find something that is the steepest descent within this ball, right? And now what you're trying to say is that the ball, which was like an axis aligned unit ball, is now this like potentially axis non-aligned ellipse that is defined by G, right? And so it like changes like your direction of steepest descent now.
That makes it so that larger parameters don't.
Exactly. Okay, so the point here is that it's sensitive to policy parameterization. If you introduce a G norm rather than a Euclidean norm, the G inverse helps you like account for different weighting along different dimensions, right? And this is what you'd often call not quite the natural gradient yet, because we haven't defined what the G is going to be. But essentially, the key idea in natural gradient is to say that policy gradient is really sensitive to parameterization. Instead, we're going to introduce some G, that G is going to do like the reweighting. Okay, everyone with me? Okay, good. So the question is, how do you choose G, right? And so what should G be? So what ideas do we have on how we should choose G? Without computing the full action, yes. Maybe one way of thinking about it is just like back to iteration, right? We talked about you really want the parameters to be weighted by how they affect the output, right? And so in the case of the policy gradient, right, your output is like your action distribution, your policy, right? So you're going from your states S to an action distribution over A's, right? And so maybe one way we can think about computing this constraint is to say that we don't want to just weight things according to the Euclidean norm, but by according to how they change the policy, right? So you want to say that weight things higher that change the policy more, and weight things lower that change the policy less, right? So what's a way we can write the dependence on the policy, right? So we want to, like, this constraint is saying keep the parameters in the Euclidean form. What I really want to do is to like keep the I want to constrain the action distribution rather than the parameter distribution. I care about the outputs, not about the parameters, right? So what's one way we could like introduce a constraint here that does this? Yeah, divergence. Great. One way of thinking about this is that rather than using this as did I post my slides? Or do you just know this already? Nice. So this is a KL divergence, right? Because the KL divergence is saying that you want to find the direction of steepest descent on the linear approximation to the objective, such that the like policy doesn't change that much, right? So you're trying to like account for like not a ball in Euclidean space because that doesn't affect the output. Like what you really care about is the effect on the action distribution, because that's the thing that's going to matter, right? And so you want things that are like not changing the action distribution that much, right? Which is what the KL divergence is, right? So do you remember the KL divergence from last lecture or 3 lectures ago? So the KL divergence, just as a recap, is expectation pi theta log pi theta by pi theta I. Yes. So intuitively, you can think of this as saying solve a linear approximation to the objective, but put a constraint on the KL divergence not changing too much, right? And so one view of doing this is trying to say, okay, we want to choose a particular G, and this is a G that considers the effect of the output. Another way that RL people often like to put this as saying that like it's like a trust region, which means that you're not letting your policy change a lot. So the argument is if your policy changes too much, it might become catastrophically bad. Catastrophically bad, it's gonna like do crazy stuff. So like don't let your policy change too much. So like optimize your expected reward objective or an approximation to it, but don't let your policy change too much. Right? Yeah.
Does forward fail divergence?
It does. I'm pretty sure we use the forward KL divergence because you don't care about things under the previous policy. You just care about things, or sorry, the reverse scale, because you don't care about things under the previous policy. You just care about things under the future policy. But I might have gotten that wrong. Let me get back to you.
Offset. I mean, I can imagine the ellipse.
Yeah. So what we're gonna do is we're gonna approximate the KL divergence with the second order Taylor approximation. And that's going to become an ellipse again. And so the nice part about the second order Taylor approximation of the KL divergence, so it's going to be theta minus theta I times some F. And this is what you're going to call the Fisher information metric. It's going to be expectation by theta of grad log by theta times grad log by theta transpose. Like the outer product of grad log pi. And so it's like, if this is dimension n and this is dimension n, this is going to be like an n by n thing. Right? And you can think of the Fisher information metric as something that tells you like how sensitive your log pi is to changes in theta. Right? And so you can show that the Fisher, like if you take the second order scale divergence of this thing, I'll link you guys to some articles that do that, but basically you can show that it reduces to this with the normalizing factor, where F is that. That's what you're gonna call your Fisher information. Yes. Yes. That's why we need all the like next two sections. Yeah. No, that's a great question. Yeah, you have to invert it, and if it's like this is like a 7 billion parameter model, you're toast. Right. So, yeah.
So here to the first thing saying that don't change your parameters so that they're outside from norm, you did not involve.
Not unit norm, the G norm. Right.
Or the very original.
Oh, sure.
Like, keep it within.
Yeah,
the
yeah.
law. Then it's saying like keep it within some G norm, or it's saying just don't change your policy.
No, this is saying that, so this is saying, the question we're asking is how do we choose the G? Right?
Right.
So what we're gonna say is that the way we're gonna choose the G is make that constraint into a KL divergence constraint. And then do a second order approximation to the KL divergence constraint. So the G is the same thing as the stat, which is the Fisher information metric. Right? And you can think of the Fisher information metric as something that tells you how sensitive the probability distribution is to changes in parameters. Right? And so like, essentially, this is going to let you like upweight things that are more sensitive and downweight things that are less sensitive. And so, point here is that we went from this G norm thing to the scale divergence thing, and then scale divergence gives you a second order approximation. Like the second order approximation of the scale divergence is this Fisher information metric, and the Fisher information metric is written over here. Right? So basically you have scale divergence, a second order approximation. This quantifies like how sensitive the probabilities are to theta choices. And now you can, apply the same machinery we had earlier, so that you get theta I plus 1 is theta I plus alpha times F inverse times grad J theta. Remind me of your name again? William. So as William was saying, this is a little tricky because you have to invert F, right? And so that's going to be a pain in the ass, but we'll like, all hope is not lost, and we will find a way to invert it. But the point I want to make is that if you compare to normal gradient descent, it's just preconditioning with this F inverse, where F is this Fisher information metric, and the Fisher information metric is telling you how sensitive is the probability distribution to like changes in parameters, right? And so it's trying to like not account for like changes in the policy parameterization as long as it doesn't affect the action distribution. And so that's what makes it go there. So this is called the natural gradient. So there's a bunch of really nice papers on it. I'll try and link you some of those, but yeah, that's the idea. We typically have a hard time computing F inverse for large problems, which is why we'll there's approximations, which is through quantitative gradient and other things, which we'll talk about next class. But we don't actually in practice invert that for huge objects. And that's what PPO is like an approximation. Okay, cool. Thank you all. See you on Thursday. Few logistics things. Project proposal next Monday. Let's have it due next Monday. I'll post some ideas for you all tomorrow. And discussion we'll do next Tuesday. We'll send out assignments, and homework we'll release next Monday. Yeah. Okay. Thank you.
Do you
want to come by office hours tomorrow? I think it's 3 to 4, but I always forget this, one sec. It's either 2 to 3 or 3 to 4. 2 to 3, Wednesday, yeah. Okay, how about you email me and we'll find it out. Okay, or post on that stem, we'll find it out. Yeah. Yes,
So was the point of like the Sham paper not going to realize that the scale of your second approximation gives you like. It's like.
so the point, the Sham paper is actually the natural policy gradient.
Okay.
The Amari paper is the natural gradient, and so the point is that you can define the natural gradient for anything that is not RL. Like it's true for any machine learning problem. And so Amari did it for any machine learning problem, and Sham took it and did it for policy gradients and showed that that is a like valid, like improving policy, like policy learning.
Has anyone tried for like the gradient problem, like where you have like high parameters that disproportionately like weight your changes, like just